This lesson is on solenoids. So we're going to imagine first a single loop of current carrying wire, and we're going to apply the first right-hand rule that we learned to opposite sides of it. So here I've got a loop here, so there's a circle, and the current is traveling this way. This is the conventional current. And just note that conventional current is not actual electron flow. It turned out that when they first came up with these rules, they thought positives traveled, so they had the current going in the wrong direction. So there are left-hand rules that go with actual current direction, but I find the left-hand rules a little bit harder to do because most of you are right-handed. But you can translate all these right-hand rules to left-hand rules for actual current. Okay, so again, back to our loop. So we're traveling in this direction. So if we look at, we're going to look at the left-hand side here. So our current is going down. So imagine your right-hand rule from before. So if my current's going down, then I end up with loops that are traveling around, and it would travel from in behind to out in front and back in behind, right? So we'd get concentric circles that look like that, which means inside the loop we're going this way. And now let's do it for the right hand side of this loop. So we're going to do it over here now, which means your thumb is going upwards and your fingers are curling, and we would see that the loop again is like this. So you can see those two circles are in opposite directions, which they should be. But here's the neat thing, is that the part that's inside the loop is going in the same direction. So it looks like here that our magnetic field inside the loop is coming out of the page. Okay. So now if we imagine an actual solenoid, which is a coiled conductor, so not just one loop, but it's, a whole bunch of loops together, and it's carrying a current, and I'm showing you that the loops at the top of the page, so these ones up here, you can see are going into the page, and at the bottom, that's where they're going out of the page. So if we think about how each of these points could create a magnetic field, so the top ones go into the page, so my thumb goes in and my fingers curl, and it turns out they curl clockwise. So each of these makes magnetic fields around them that go clockwise, which means since the bottom of the page is out of the page, that means we're going to go counterclockwise. And again, let's make sure we draw arrows here inside so it's nice and easy to look at. And look at that. We end up with ones that are going all in the same direction on the interior. And if you think about it, these magnetic fields are all going to interact. So if we started to draw another one, say down here, well, it would end up being interfering with the one out here, and it would kind of just continue into itself. So we have one in the middle, perfectly in the middle. It's going to end up being this perfectly straight thing. And ones that kind of go outside it that look like that. So really we're going to end up with a bunch of things that do this, which should kind of remind you of the bar magnet drawings we've done earlier. So let's think of that bar magnet, because the solenoid, it turns out, is an example of what we call an electromagnet, which is a magnetic field produced by an electric current. And in this case, it resembles a bar magnet. Because if you think about it, remember our bar magnet has things that come out of the north and go into the south. And it kind of looks fairly similar. We can see pretty good similarity to the field that's produced there. I'll add the arrows on the outside of this one just so you can kind of see a little better. So there's also a right-hand rule for these coiled conductors. So we don't have to actually think about the individual parts of the coil every time to do this. It turns out we can actually just use a particular rule itself. So if we curl our fingers in the direction of the current carrying coil, in this case in the top part is going into the page, so make sure your fingers are curling so that into the top of the page it's going in, right? So at the top of the coil into the page. So we're curling this way, and you can see my thumb is in this direction, so that must be the direction of the north magnetic field, which is concurrent with what we've seen so far. And that concludes the lesson for solenoids. So you've got two right-hand rules now, one for straight conductors and one for a coiled conductor.